The fourth planet from the Sun, Mars, has historically been the source of constant awe and mystery. 19th century astronomers believe they saw a vast network of canals crisscrossing the surface of Mars, connecting huge Martian cities, while science fiction writers and filmmakers have given us a wealth of stories involving evil Martians coming to conquer Earth and destroy its inhabitants. Ironically, the recent discovery by NASA scientists of real life forms on Mars has sparked not only a storm of controversy over the possibility of life on other planets, but has also generated more public interest than ever before in Mars exploration and space in general. This program presents a brief history of the past exploration of Mars and the fleet of international spacecraft currently planned to explore Mars and search for life over the next few years. There are also plans for possible future human exploration missions, ultimately establishing a permanent human presence on that distant red planet. In 1965, NASA's Mariner 4 became the first spacecraft to fly past Mars, taking the first close-up photos of the red planet. It was followed in 1969 by Mariners 6 and 7, revealing many unique features. In 1971, Mariner 9 returned photos of canyons, volcanoes, and dried riverbeds. In 1976, 2 Viking spacecraft were sent for a more detailed exploration of Mars. Once in Martian orbit, both spacecraft detached a lander that soft landed on the surface. The orbiters provided a detailed mapping of the surface, while the landers conducted a variety of experiments on the climate, soil, atmosphere, and searched for life. From the tremendous amount of data received from the Mariner and Viking probes, the history of Mars is slowly being revealed.
Mars and Earth started to form about 4.5 billion years ago. And for their first 500 million years of existence, Earth and Mars had almost the same environment. 4 billion years ago, they were both wet and warm with dense atmospheres of carbon dioxide. And then life began to develop on Earth. And the atmosphere on Mars changed. And Mars became cold and dry with a very thin atmosphere of carbon dioxide. And Earth is teeming with life. We need to know. We need to understand this.
There was a lot of water on Mars, and today there's essentially no liquid water on the surface. And of course, that is a remarkable change in climate, and to the extent we can understand what it was that caused that change, it will help us better understand the evolution of our own climate here on Earth.
A number of extremely important issues on Earth, like the ozone hole, like the nuclear winter, like the greenhouse effect, were invented by planetary scientists who had been working on planetary atmospheres. And it came back to Earth. So it's very clear that there is a unification of the science of the planets from this point of view. So therefore, it's clear that there is a very important science reason to go to Mars.
In 1992, NASA launched the Mars Observer, a large, complex, billion-dollar spacecraft that was to provide detailed information on the Martian surface, atmosphere, magnetic and gravitational fields. Unfortunately, just as the spacecraft was about to enter into an orbit around Mars, contact was suddenly lost, and the mission failed. In the wake of such a high-profile failure, and in an effort to maintain congressional funding, NASA had to rethink its policy of big-dollar planetary probes. NASA is now using the technologies of electronics and miniaturization to build a series of small, inexpensive probes so that many of them can be sent to explore planets on a more aggressive basis, and the success of the mission does not rely on the success of a single probe.
We are now planning on sending 2 probes to Mars about every other year when the launch window opens up, just from the United States. So this faster, better, cheaper technology is going to allow us to get much more information sooner for much lower cost And it'll help us understand, is there a potential for scientific benefit on Mars? Is there a potential for economic benefit if humans were to go there? And it'll help us make decisions. Should we take the next bold step and send a human exploration mission?
The first two spacecraft to venture to Mars in over 20 years will be a small and highly advanced orbiter called Mars Global Surveyor and a lander called Mars Pathfinder. Both will be arriving at Mars in mid to late 1997.
Mars Global Surveyor arrives, goes into a big looping orbit by firing its engine, and then uses the atmosphere of Mars, skims through the atmosphere of Mars on each orbit until the orbit is made smaller and smaller until it's in a circular polar orbit, and then it maps the surface of Mars for 2 years and watches the seasons pass and takes close-up pictures and gets laser altimeter measurements so we can tell how high the mountains are and how deep the canyons are, and tells us what Mars is made out of.
A lander which will carry down to the surface of Mars on July 4th, 1997, a small micro-rover, 25 pounds, running on 8 watts, which will be able to maneuver for the first time on the surface of Mars with a set of cameras and a small spectrometer which can analyze the composition of various kinds of rocks that it will find on the surface of Mars.
Unlike all prior nationalistic single-country efforts in the past, this probe will carry an international package of scientific instruments, breaking new ground in the cooperative exploration of Mars.
We from Max Planck Institute for Germany for chemistry in Germany have a little device on it which allows to make chemical analysis of the rocks and soils to which these little vehicle will travel to. Actually, this experiment is done in cooperation with a group here in the United States, a group from Chicago.
We have the Finns from Finland have put little magnets on places so that it'll gather the dust, and the camera can take pictures and see how much dust is clinging to the magnets, and they're Finnish magnets. We have international participation in the weather station on Mars Pathfinder, and the Germans are providing part of the Mars Pathfinder camera. So there's considerable international participation.
The Pathfinder's primary mission will be to test the teleremote sensing from the Earth-based control room, as well as conducting several experiments that will help to improve the efficiency of future robotic rover missions. In addition, the Pathfinder will also try to confirm the discovery of organic molecules and other chemical compounds found in meteorite samples that came from Mars, strongly suggesting life may have existed there. The Pathfinder will attempt this by analyzing the composition and mineralogy of rock and soil samples from many new locations. The orbiter will begin the highly detailed mapping of the surface, necessary to determine future landing sites of probes and human exploration missions. The Russians, in cooperation with many European nations, have plans to launch a large probe to Mars called Mars 96. This ambitious mission will study the processes responsible for the evolution of the Martian atmosphere, climate, and surface.
The next mission which we were planning was to go to Mars, to place an orbiter in the orbit around Mars, and to send to the surface of Mars a few smaller probes. We called them penetrators, so they could penetrate through the upper layer of the soil and do some measurements for deeper constituents. And small stations which could stay on the surface of Mars do meteorological measurements, some chemical analysis or seismic analysis.
On this large spacecraft, which carries something like 450 kilos of science, which is enormous, there are instruments which have been built not only by Russian scientists but also by European scientists.
Mars 96 will carry 4 landers, in fact 2 penetrators and 2 small stations. The penetrator hit the surface rather hard. The idea behind this is to go deep, to go a couple of meters inside the Martian regolith and study there, again, chemical composition, but also these penetrators carry seismometers and magnetometers and a number of other instruments.
Those stations don't have the power to send messages to Earth. So their messages have to be relayed. So there is one relay on the American spacecraft Mars Global Surveyor and one relay on the Russian spacecraft, which both will be in orbit around Mars. Those relays are being provided by France, and they are operated both by the United States and by the Russians, which are working together in the frame of an international agreement.
In 1998, a Japanese probe is scheduled to be launched called Planet B. It will rendezvous with Mars in 1999 and operate for at least 2 years in orbit.
Planet B is a spacecraft by the Japanese space science organization called ISOS, and it's a mission to the Martian atmosphere and magnetosphere. The main objective is to study the interaction between the Martian atmosphere and the solar wind. Solar wind is the flow of plasma from the sun, and since the Mars does not have the magnetic field, or even if it does have, it's a very weak magnetic field, the solar wind and the Martian atmosphere get mixed in the ionosphere and produces various interactions. And the main objective of this Planet B mission is to study the mechanism of this interaction.
This spacecraft will return data on the magnetic field, the interaction between the solar wind and atmosphere, the magnitude of dust storms, as well as images of the surface. This Japanese mission will also have an international involvement in the scientific instrument package it will carry to Mars.
Take this Planet B, for example. It already has instrument from Canada, plasma analyzer, and another plasma analyzer from Sweden, and a dust counter from Germany.
This Japanese mission has an American instrument on board, a mass spectrometer, a very high technology instrument that is being built at the NASA Goddard Space Flight Center and provided to the Japanese Space Agency, and in return the US scientists get the data from the Japanese Mars mission.
Planet B will be launched in August, which is actually earlier than the launch window to the planet Mars in that time period. The reason is that according to some Japanese political agreement, there is certain the launch windows in which only in which we can launch a spacecraft. This is due to the agreement with the fishermen who does not like to have all these rockets dropped in the fishing area, so that the spacecraft will have to orbit around the Earth for some time before it really gets off.
Mapping and detailing the interaction between the magnetic field and solar wind particles can provide invaluable information regarding our understanding of the dynamics and evolution of the Martian atmosphere. Also to be launched in 1998 are 2 more probes to be sent by NASA, called Mars Surveyor 98. One probe will be an orbiter and continue the survey work started by the Mars Global Surveyor.
The 1998 orbiter will carry a large instrument to look at the atmosphere, and will carry an instrument to look for resources on the surface, mainly water.
The other probe will perform a soft landing on the Martian surface. It will conduct an extensive search for water, as well as performing numerous experiments to understand the planet's climate history. The search for water on Mars is the necessary first step in the overall search for life or evidence of past life on the planet.
Our idea of the origin of life on Earth suggests that life appeared very rapidly on the Earth once the proper conditions were met. And the proper conditions were basically the presence of liquid water on the surface of the planet. So our conception of life in the universe is that if you had a planet that was Earth-like and it had liquid water, then life will be a rapidly emerging phenomenon on that planet. That's our current bias in terms of our approach to the question of life. Well, Mars is a direct test of that. We look at Mars, we see that here's an Earth-like planet. It had liquid water. We should expect then that, geologically speaking, life would have rapidly emerged on that planet.
The lander is going to land near the South Pole and use a robot arm to dig down through the layers of terrain at the South Pole, sort of like doing tree ring studies on the Earth. We expect to find a little layer of ice and then a layer of dust and a layer of ice and a layer of dust, because every year it sort of snows and makes ice, and then the dust storms come and put dust over that. So by digging down through this, we'll be able to tell the climate history of Mars.
The permafrost on Mars is an excellent target for the search for life, because even when Mars was warmer, the polar regions would still have been very cold, and it's likely that, just like on Earth, organisms and sediment would have been frozen into that permafrost. And on Mars, they would have remained frozen for all these billions of years. The notion of going to the South Polar region on Mars and drilling down and pulling up samples and looking in those samples for frozen but dead Martians, I think, is an important goal.
By gaining new knowledge about the ice at the poles, computer-generated models could be made on how much ice and water might be present at the equator and other places throughout the planet. This data may eventually be used by human exploration missions digging for necessary water supplies.
Certainly after the Planet B and all these international missions in '98, people will come up with the idea of doing things better. And I'm quite sure that the Mars mission will continue with much improved instrumentation and more focused ideas. So that 98 is going to be the great year for the Mars exploration.
NASA has definite and committed plans to send more spacecraft to Mars in 2001, 2003, and 2005, although their designs and goals are still under discussion.
The decisions for future missions for 2001, 2003, and 2005 have not been made yet. The instruments have not been selected yet. We know more or less which instrument types we want to fly, we want to launch to study Mars. But the details have not been decided on, nor have the principal investigators been selected. That means at this stage we don't know which country provides which instrument. But as you can see in this meeting here, we have participants from all over the world coming to this meeting and discussing science instruments, science questions with us.
In 2001, 2 spacecraft will be sent to Mars. An orbiter will continue mapping and searching for resources in the surface, and a soft lander that may perform chemical analyses of soil samples for signs of life.
In 2001, our lander is going to be landing in the ancient terrain of Mars, hopefully near an ancient lake bed. So we'll be able to see if there was ever, maybe, be able to see if there was ever life on Mars, see if we can find some indications of, if you find fossil scum around the edge of the lake bed, you know there was life there. Maybe we probably won't find that, but maybe we can find some indications.
Searching for life on Mars is going to be a challenge, because not only do we have to find a place on Mars where life could have survived, but more importantly, we have to find a place on Mars where fossil evidence of that life would be preserved. And that's the challenge, finding an environment that would preserve evidence of life. And a lake is also a good place for fossilization, because as organisms die in the lake, their bodies settle down to the bottom and get preserved in the sediments so that billions of years later they're still there.
Also in 2001, the Russians and Europeans are planning to collaborate together on a possible mission to deliver a robotic rover to the Martian surface.
Well, the major future project, which is still under discussion, is called Mars Together. The idea was that in the year of 2001, we could have a major expedition to Mars, unmanned, robotic, delivering quite sophisticated Mars rover. Russian word for that would be Marsahod. And the idea was to use one of powerful Russian launchers like Proton, or maybe a little bit smaller.
Perhaps the greatest obstacle facing this rover mission is the ever-dwindling supply of money and the changing political climate in Russia.
The first difficulty is that the Russians are in a terrible economic state, and at the same time they don't have any more priority for the space activities. So they maintain the man in space activity because they have an agreement with the United States and with other international partners like Europe or Japan. And that's because this provides them with money.
Planetary Society has tried to suggest that the use of this Russian Marsicod, the Mars rover that they've built, a unique capability in the world as a rover that can travel over many miles on the Martian surface, is something that would be very good for us to adopt in a joint mission, because we could get the benefits of this rover, and the Russians could get the benefit of our electronics to instrument it, and we could do this thing together. It would really be a great asset for future exploration of Mars.
Here's the U.S. Mars program. It only has this much money to spend, and within those resources, we can't see how we can get a really capable rover that's capable of going tens to hundreds of kilometers and has, plenty of payload, can pick up plenty of samples. We can't see how we can do that. But there's a real simple way to do that, and that's to just collaborate with the Russians, who are planning to do it anyway.
The U.S. mission scheduled for launch in 2003 may well involve the delivery of a Russian Marsicod to the Martian surface as a possible precursor for a future rover that will gather rock and soil samples to be packaged and returned on a later mission.
In terms of how rovers are going to have to operate on Mars in 2003, 2005, whenever we put them there, they're going to have to be a lot more autonomous than we currently have made them. The rover's probably only going to be able to send information to Earth or get information from Earth a few times a day. So if you want to be able to do a 100-kilometer traverse in a year, you obviously have got to get a lot better at doing things autonomously.
By far the most ambitious international collaborative effort currently in the planning stages is the Inter-MarsNet probe.
Inter-MarsNet is a proposal of a number of European scientists which consist of a number of small test stations which would be placed on the ground of Mars in 2003.
Since this Inter-MarsNet concept, there will be only 3 stations, 3 landers. The landers will be provided, are planned to be provided by NASA, while ESA would provide the launcher, an Ariane 5, and an orbiter, and very dedicated orbiter, not just for data transmission, but also for science, especially in respect to atmospheric sciences.
The necessary next step in the exploration of Mars is to be able to bring back a sample of rock and soil so that more extensive studies could then be conducted in the search for life. Oddly enough, there have been a number of meteorite samples discovered that have recently been suggested to come from Mars.
During the last 20 years, 15 to 20 years, the idea was brought up that a small class of meteorites might be of Martian origin. They are igneous rocks. And I started out just working at the time when there was nothing known. And I said to myself, okay, either this parent body of the SNC must be a very interesting object, or it's planet Mars.
There's sort of a group of reasons that we think these samples came from Mars. They were originally looked at as being somewhat strange from normal meteorites in that they look very similar to rocks from the Earth that form in volcanic-type processes, igneous processes. And they were found to be quite young, on the order of 1 billion years old or less. Now, that might seem old, but it's actually quite young on solar system timescales.
A high-speed meteor impacting on the Martian surface could easily have caused thousands of tons of soil and rock to be ejected from the planet's surface. The ejected samples no doubt spent millions of years in space before landing at various sites on Earth.
The one thing that really ties these samples to Mars is some of them in this impact event that ejected them partially melted. This impact event is a violent process. It shocked these samples intensely and caused them to partially melt. And then, so we have these little pools of what was once melted and has now formed a glass. You see these little pods of this shock-melted stuff. And in this shock-melted stuff are essentially samples of the current Martian atmosphere.
Colleagues here in the United States discovered that these shergotides contain a component of rare gases with element and isotope ratios unknown in any other meteorites, but identical both in elemental and isotope ratios to the Martian atmosphere as known from the Viking mission.
We see essentially a fingerprint of these chemical signatures implanted into this rock. Sort of strange elements like xenon and krypton and argon and nitrogen, we see very distinctive signatures in this rock that pretty clearly tie it to the planet Mars. And that is the most convincing evidence that specifically links these samples to the planet Mars.
Among the tens of thousands of meteorites that have been collected over the years, there are a little more than a dozen of these Martian meteorite samples that have been discovered so far, and some of them were found over 100 years ago. In what may be the single greatest discovery in the history of humanity, scientists from NASA and Stanford University recently revealed their findings of the remains of life forms within these Martian meteorites. Analyzing a meteorite sample discovered in Antarctica in 1984, these scientists claim that certain structures found in the rock are in reality fossils of single-celled organisms similar to ancient life forms here on Earth, and also found certain organic molecules in the rock that may have been the residue of these life forms. However, there are many noted scientists that dispute these claims and strongly urge further studies into the search for life. Among the points of controversy are the fact that there are many non-biological causes for the organic molecules found in these meteorite samples, and there were no distinguishable body parts, cell parts, DNA imprints, cell division, etc. found in these presumed fossilized remains. Perhaps one of the strongest points of contention are that these remains were found in igneous rock.
So on Earth, there are no forms of life in igneous rocks. Where you find the ancient life on Earth are sedimentary rocks, which were once in form of individual minerals and only compacted later on by temperature and pressure. Those igneous rocks are the wrong samples to look for remnants of life.
By only taking the samples that are sent to Earth by ejection, we will probably get a very biased sampling of the Martian surface. For example, a sedimentary rock may not survive. A rock that formed in an ancient lake bed, for example, may not be able to get out by a process like that. And these are exactly the kind of rocks we want to study to understand early climate, potential for early life, early geologic processes that may not be going on today. And that is the reason to still go to Mars, even though we already have these samples in our hand. I think that it's very clear that we need to sample other types of terrains, and we need to have the samples in context.
The engineering and technological demands for a Mars sample return would be enormous. Not only would there have to be a launcher developed for a heavy payload, but also a need for a fully robotic rover that could gather samples and package them, as well as a fully automated vehicle to return the samples back to Earth.
And so we need to know something about where we're going to land. So that's why in 98 and 01 and 03, we want to send our landers to the interesting places, and then we can say, oh boy, we want a piece of this. So we'll go back and land there again and then pick up a piece of that. Now we also might have, like in 2005, we might have rovers go around and collect samples and put them in a box, and then in 2007 come and get the box and take it home. So we don't know really how it's quite designed yet.
One of the most difficult technical aspects of a sample return mission is the need to provide a fully automatic return vehicle that could carry the samples back to Earth.
Another thing we're working on is maybe making fuel for the rocket out of the atmosphere of Mars. And so we're taking the atmosphere and turning it into a chemical plant and producing fuel for the return. So that's one of the options we're looking at. So there's a lot of technology that we're trying to advance to be able to do these missions within the cost constraints that we have.
When we bring samples back from Mars, we want to be very careful and cautious to make sure that there's nothing in that sample that could be a danger to the biosphere, not just to humans, but to anything. We all have seen examples where organisms introduced into a new place where they've never been before have wreaked havoc on the ecosystems there. So for that reason, the current plan is that when a sample is brought back to Mars, we treat it as if it's full of pathogenic, dangerous microorganisms. We treat it like it's a jar of Ebola or something.
Some scientists even argue that these samples should be returned to a laboratory on board the International Space Station first for analysis, then sent to Earth only after its safe handling was assured. Whatever form a sample return mission may eventually take, an international collaborative effort to acquire a sample would certainly be a superior mission than if any one country tried to do it themselves.
Major component which Russia can contribute launchers. If, for example, we would get a Proton would easily accommodate for almost all the requirements which we are discussing now for Mars sample return.
The potential contribution to such a future collaborative sample return mission by Russia would include not only the launcher, but also their unique rover that's already been field tested on the lunar surface, in addition to their valuable experience of sample return technology with lunar samples.
One prominent military industry in St. Petersburg during Cold War was designing not only modern tanks, but because of the hobby of chief designer, was investing in first in a lunar rover and then in Mars rover. So mechanical part of rover is the area of special Russian expertise too. So if we would be able to assemble, these individual components of Russian competence plus Russian launcher, it would be already very essential contribution.
Cooperation with the European Space Agency could potentially benefit an American effort by increased development of state-of-the-art computer technology for the rovers, as well as providing communications and ground control expertise.
The European Space Agency is a relatively young agency. Among the items they can bring to the table are, for instance, excellent launch vehicles, Ariane launch vehicle. They can bring to the table the expertise of more than a dozen European countries, the technologies developed in those countries, and the science expertise of different countries in Europe. And it's proven extremely beneficial to collaborate with Europe on practically every mission NASA has had for solar system exploration.
Once these Martian rock and soil samples have been analyzed, our knowledge and understanding of the red planet will allow us to take that next bold step in the study of Mars, a human exploration mission to the Martian surface.
I could foresee a day, perhaps 10 years from now, as early as 10 years from now, where we may want to decide there's a compelling reason to go to Mars because we got the mission cost down to an affordable level, and we see scientific benefit for early human exploration. And these explorations could take place within my working lifetime.
The Apollo moon missions were the result of a competitive challenge between superpowers. Unlike Apollo, the reasons to go to Mars will largely be the result of a unified, scientific, cooperative, and collaborative effort.
When it comes to thinking about human visits somewhere, I think there are great lessons to be learned from the Apollo program. I think we owe it to ourselves and future generations to make a commitment that this should be an expanding endeavor and not one that peaks and then levels off or ceases in operation. We shouldn't go to Mars once, twice, 3 times, and then allow a future Congress to say, well, we've done that, let's not do that anymore, let's shift our emphasis somewhere else.
Given the current geopolitical and economic conditions of the world, it would seem highly unlikely that any one nation alone would assume the tremendous financial responsibilities and develop the technologies required for such a human exploration mission to Mars. Unlike the Apollo crews, which consisted only of American white male astronauts, the crew of a mission to Mars will likely involve men and women, as well as representatives from a variety of nations.
Long-range scientific questions are the realm of the scientific community in the world. There are clearly issues of national concern, technologies that could help the economy, knowledge that will turn around whole industries. On these areas, we must, in the United States, look at our national priorities first. But after we define national priorities, we certainly can cooperate. Each country has to decide what does it feel is important to its future that it must do alone. But after one does that, there's still a lot of room for countries to work together.
When we get to human missions, it's almost certain we're going to have an international endeavor, just like International Space Station Alpha. I mean, that's got Europeans, it's got Japanese, it's got Russians, it's got US, and I think that's the way we'll be going to Mars with people.
Just like it's not important in the long range of things where Columbus came from when he came to discover America, as it said. Was he Italian? Was he financed by Spain? Was he using a Portuguese crew? What difference does it make? That was an international mission. But somebody paid for it, somebody else contributed to it, and it had all of these other aspects.
The motivation for exploring Mars politically is cooperation, not competition. And cooperation by its nature is not a goal-oriented task, it's a process-oriented task. From a political point of view, what's important is not going to Mars and coming back, but the process of working together to go to Mars. So, in fact, the logic forces you the other way around. The best way to make Mars a beacon of international cooperation is to have the mission take as long as possible. Stretch it out.
The difficulty that America and Europe gets into when we try to collaborate is that America changes its mind all the time. We have a presidential election, we get a new Congress, they're not interested in doing that anymore, they try to cancel that program. The Europeans, meanwhile, are going along in a process that has been defined for 10 years, and they're going through their part of the deal. They don't back out on their agreements, and then America's always changing their mind, and it drives them crazy, and for good reason.
Sending a joint mission of all the great space power to Mars, meaning a symbol of unity of mankind, has a lot of appeal. The taxpayer in the world will receive an expedition to Mars like something enthusiastic and something important, something fundamentally basic like Apollo, which was a symbol of the power of man over nature through science. Then it may happen.
Just as the Apollo program put thousands of people to work across the country in achieving the technological means to land a man on the moon, an effort of equal magnitude will also be needed to address the technological challenges necessary to make a human exploration mission to Mars practical.
The most critical technology that has to be developed is low-cost, reliable Earth-to-orbit access. This is the major barrier to getting to Mars. Second thing we have to do is to learn how to live off the land. We cannot afford to take all our breathing gases with us for a 2 to 3 year mission. We cannot afford to take all our food with us. We've got to learn how to live off the land.
The way you're going to do human missions is you're going to land a capsule, a base, probably an opportunity before you land the people. And so the people are going to get on the surface of Mars, go to the base, you know, surface rendezvous with the base, drive a truck or whatever, open the doors and turn on the lights. That's the sensible way to do it.
The atmosphere on Mars, however thin, still has carbon dioxide. We can convert that carbon dioxide with a little added hydrogen into methane fuel and oxygen for breathing gases. Perhaps there's water on Mars. We could convert that into a very high energy fuel, hydrogen and oxygen, and we could also have water to drink. We could have oxygen to breathe.
Because of the distances involved between the planets and changing launch windows, a human exploration mission would most likely last well over 2 years. For such a mission to last for so long in a harsh and unyielding environment, the new technologies being developed may ultimately be useful and applicable to how humans live here on Earth.
We need to take seeds with us and not foodstuffs, because foodstuffs are very heavy. So we'd like to be able to learn how to plant foodstuffs on Mars in the Martian soil, in the Martian environment. And then we'd like to figure out how to have what's called a regenerative life support system, so that we could recycle the air we breathe and we could recycle the water we drink. If we could overcome these issues, we're on our way to Mars.
One of the primary goals of such a mission would be the continued search for life forms or fossils. These would provide information on how life may have begun not only on Mars, but here on Earth as well.
One of the most compelling questions about Mars is, was there life, and searching for that life. But we don't really know what we're looking for. We can't even come up with a rigorous definition of life. In some sense, when people ask me, how are you going to search for life if you can't define it? The answer is, well, we'll know it when we see it. And what's really saying is that you're relying on sort of the holistic, intuitive approach to exploration that humans can bring. You don't have a well-defined task that you can program into a computer and say, make this measurement, take this analysis, and then tell me what you find. It's a much more interactive process, searching for life, searching for fossils. And certainly right now, we only know how to do that with human beings.
Another one of the goals of a human exploration mission might be to assess the possibilities of maintaining a long-term presence there. Because of the available resources on Mars, it would be relatively easy to establish a permanent or semi-permanent base there.
I really think what this nation, what the United States has to do is to define how we would lead international efforts to establish capabilities for settlement, colonization, realizing the economic benefits and the scientific return from the opportunities at Mars. Not just say we're going to do this internationally. Russia, what do you think? France, what do you think? It'll be a jumbled mess of self-interested projections. What we have to do is look at a great overall strategy for this nation that invites the cooperation and the participation of other nations.
There are philosophical aspects in a future international venture of that kind, like, for example, what kind of society will the people on the surface of Mars live in? Will it be a free enterprise society? Will it be a communist society? And there are several interesting aspects of that to be studied. The other aspect is whether you will choose what kind of selection of astronauts will you make? Will they be all white? Will they be all yellow? Or a mixture of them, most likely? That's a very interesting question to assess on these big-scale ventures.
Right now, we're sending robots to Mars. Well, why are we sending robots to Mars? In my mind, we're sending robots to Mars as scouts. They're going to check it out so that that can be followed by humans. Why are humans going to Mars? Humans are going to Mars to see if it could be a long-term home for life. We're also scouts. We're scouts for the broader phenomenon called life. Think of them as steps along the way, and the ultimate goal, at least in my mind, is another planet that has life.
Some scientists have even proposed the possibility of someday terraforming Mars, or making Mars more Earth-like, with a warmer climate and even an oxygen atmosphere.
The key step in getting the process going and preparing Mars for life is to warm it up a little bit. And I think the best way to do that is the way we're already warming up the Earth. It's probably not a good idea on Earth, but if we were to produce on Mars the same compounds we're producing on Earth, or maybe variants of them that are not harmful to ozone, compounds such as fluorinated carbon compounds. These compounds can have thousands of times the efficiency of CO2 in creating a greenhouse effect. And if we could produce them on Mars, they would warm up the planet enough to start this process going and allow us to introduce life.
Once Mars has a warmer, thicker atmosphere, comprising mostly of the greenhouse gas carbon dioxide, then the deadly ultraviolet rays and solar wind particles would be blocked. At that time, tough tundra-like plants could be imported from Earth to convert the carbon dioxide to oxygen on a large scale. Like the Apollo program that spearheaded the American technological boom of the 70s and 80s, the technological benefits to humanity of Mars exploration are potentially beyond our dreams. In the end, the possibilities are endless and bounded only by the limits of our imagination.
I think that there is an additional benefit which is not a technical, not a science benefit. And that's a benefit in terms of we are, after all, one planet. And we are, after all, talking about getting off our planet. And especially once we get off our planet, especially once there's a colony on another planet, we no longer, nation boundaries start to become really insignificant. Because I really think that the new world order isn't going to be, you know, America über alles. It's going to be maybe Earth über alles. You know, it's going to be an order of where nations actually don't even mean anything anymore, and what means something is what planet you're from.
What we enjoy most, I mean, as a scientist, is that by getting together, we can have better ideas. You see, the people are brought up in different environments and different educational backgrounds, and they have their own different ideas about what should be done and what to do. And when these people from different countries get together with different backgrounds, different cultures mix. And that is the most interesting part. And with that, we can come up with the greater ideas for the exploration. Of course, I'm not disliking the benefit of financial, citing the financial benefit and technological benefit. All these are there. But to us, the greatest fun is the mixing of the culture.
Exploration is written into the genetic code of every American. We're just on the eve of unbelievable scientific findings on Mars. We're going to have unbelievable knowledge we'll get back from Mars to see if there's any potential scientific or economic benefit in going there. And that's what we're all about at NASA. We're about dreams and visions. And while we undertake a logical sequence to get towards these dreams, we bring back economic benefits and intellectual benefits to make our life richer on Earth. It's not spending money in space, it's enriching life on Earth, and that's what we're all about.